So when I wrote this book, it's called The Mathematician, so people were coming to me and saying, so what's the answer? I said, well, it's not a simple yes or no. And in fact, you will see that I argue that the question is more important than the answer. Now, I want to just make one statement right at the beginning so that nobody misunderstands me. This is not a talk about God. This is a phrase coined by physicist James Jeans in the last century, where he basically asked, how come that mathematics is as powerful as it is in terms of explaining the universe? So let me start by saying, posing the problem. So the problem has been termed the unreasonable effectiveness of mathematics. By the way, is there a place where I can stand without blocking? Maybe on this side, no? So here is how Einstein put it once. He said, how is it possible that mathematics, a product of human thought that is independent of experience, fits so excellently the objects of physical reality? You will notice that in addition to this being a question, Einstein actually makes here a statement too. Namely, he says that mathematics is a product of human thought that is independent of reality, and I'm going to come back to that. This is Eugene Wigner, Nobel laureate in physics, who coined the phrase the unreasonable effectiveness of mathematics. And he once said, the miracle of the appropriateness of the language of mathematics to the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. Now, what did they mean by this? And let me maybe just grab the pointer from here. So let me give a few examples. So about 400 years ago, there was this astronomer, Johannes Kepler, and he observed the motion of the planets, and his observations were spectacular for the time that he made them. But by today's standards, they were rather scanty. They were accurate to about 4%. So they were very good for 400 years ago, horrible for today. Yet from these rather horrible by today's standards observations, Sir Isaac Newton was able to formulate a mathematical law of gravity. And this law, already by the 1950s, was found to be accurate to better than 1 part in a million. So how is it possible that Newton took observations that were as bad as that and was able to formulate a mathematical law that explained observations to much better than the observations on which the law was actually based? Furthermore, in 2007, a group of physicists from University of Washington, Seattle, actually managed to show that this inverse square law holds true down to a distance of 56 microns. This is a spectacular experiment in itself, but you realize that this is a distance on which Newton could have had no idea that his law should hold true to a distance of this kind. So how is that possible? Let me give you another example. We have an incredible theory of electromagnetism. It's called quantum electrodynamics. In this theory, for example, electrons, they have a small magnetic moment. They act like small magnets. We have used this theory, QED was used, to calculate the magnetic moment of the electron. And it was calculated using the theory to an accuracy of some parts per trillion. And then in 2006, again in a spectacular experiment produced at Harvard, they managed to measure the magnetic moment of the electron also to parts per trillion. And the two results agree to better than 8 parts per trillion. This is how good our theory of electrodynamics is. And by the way, had I given this talk maybe 10 years ago, I might have had to give you a little bit of feeling of what a trillion is, but that's no longer needed. It's the size of our annual deficit, so everybody now has a good intuitive feeling for $1 trillion. I want to give you another example that is perhaps less known, although this is a group of mathematicians, so maybe to you it is known. In the 1860s, nobody knew what atoms were. Lord Kelvin was still William Thomson at that time, but later became Lord Kelvin, was fascinated by smoke rings because they were quite stable and they could oscillate in certain ways, and those were properties that were nice to have for atoms. So he thought that maybe atoms were really knotted tubes of ether. Ether was that substance that was supposed to permeate everything. And so he wanted to create a theory of atoms in which atoms were these knotted tubes of ether. I don't need to tell you what a mathematical knot is. It's the same as a knot in a string, but with the two ends spliced, so there are no loose ends. So basically what he would have liked to do is something like, like to say that the unknot is maybe the hydrogen atom, and the trefoil knot is maybe the carbon atom, and the figure 8 knot is maybe the oxygen atom, and so on. But in order to be able to do that, he had to be able to classify knots from a topological perspective. Because nobody knew how to classify knots at the time. I mean, for example, what does that mean? It means, how do I know that this knot is not the same as this knot? I can manipulate one into the other. So, to actually do that job, his close friend, mathematician Peter Guthrie Tate, actually started classifying knots. And he worked for about 20 years. P.G. Tate worked, and in 20 years, all he managed to classify were knots with up to 10 crossings. You see, I mean, this knot has no crossing, this has 3, this has 4, there are a few that have 5, then there's some that have 6, a couple that have 7, and so on. He managed to classify those up to 10 crossings. So 20 years of work, he classified only up to 10 crossings. I mean, you understand there can be an infinite number of crossings. But that's all he managed. Now, by the time he finished his work, after 20 years, everybody knew this was not the theory of atoms. At that point, other things started happening and people already developed other models for atoms. So you might have thought that this field will be abandoned because the original motivation wasn't there. Why should anybody care to look about this? But, and I don't need to tell you this is exactly when mathematicians got really interested in this. Because they didn't care that there is no motivation. They just wanted to work on knots. So they started working on knots, and over decades, all kinds of wonderful work has been done. So in particular, for example, let me give an example here. John Horton Conway, whom you all know, found these beautiful transformations that, how do you go from a crossing to a non-crossing? So, if these are real strings, I know how to do it. I will cut here and here, I will glue them the wrong way, and I go from here to here. But Conway, managed to do these mathematical manipulations that transform you from this to this. Then in 1984, something very dramatic happened, which was that Vaughan Jones, who is a mathematician at Berkeley from New Zealand, had this breakthrough where he found the Jones polynomial. So these are these algebraic expressions that are a bit like fingerprints of knots. I mean, they classify knots. And since then, there have been many other polynomials that were found, and the Fields Medal was given a few years ago, and so on, for this work on knots and so on. So they did all these things, but really with no application whatsoever in mind. Mathematicians were just extremely excited to find all these polynomials, and to be able to classify knots and do all this theory of knots and so on. And then a number of things happened. Biology started studying the DNA. And the DNA, I remind you, is this double helical structure, which is knotted in very complex ways and so on. Now, what happens when a cell divides? When a cell divides, the DNA is supposed to copy itself, to create its daughter DNA. But in order to do that, it needs to unknot itself first to do that. And the way it does that is that enzymes manage to actually pass one strand of DNA through the other, basically. Basically, they create a break, they pass, and they create and they put it back. Essentially, they do this Conway operation, only to the real thing. So suddenly, biologists discovered that they could actually employ mathematicians to show them DNA configurations, and mathematicians could tell them the rate at which the enzymes are working, because they knew what mathematical operations are needed to transform from one configuration to the other. The second thing that happened, that I'm sure you all heard of, is the development of string theory, or now is better known as M theory. But basically the idea there is, the basic idea is simple, but unfortunately the mathematics is not. The basic idea says that there are these entities that are called strings, which are a little bit like rubber bands. And all the particles that we know and love, like the electron, the quark, and so on, they are just different vibration modes of these strings. So, you know, like you pluck a violin string, you get a series of notes. You pluck this string, you can get all the spectrum of particles that we like. Now, particles also interact. And so, you know, and this is just a schematic description of one such interaction. So, two string theorists, Andrew Strominger and Qumran Vafa, actually showed that to discuss these interactions, what has become extremely useful is the Jones polynomial. That thing in knot theory which was created with no application whatsoever in mind. So how does this happen? That, you know, that mathematicians sit down, and I'm sure there are many of them here in this room, and they develop entire branches of mathematics with absolutely no application in mind, and yet decades, sometimes centuries later, those precise branches are found to provide the explanation for real phenomena. How does that happen? So, I have a very distinguished colleague, some of you may at least heard of him, maybe you even know him, Roger Penrose. He's a, let's call him mathematical physicist. And he once described this as 3 worlds and 3 mysteries. So here are the 3 worlds. One is the physical world. That's the world in which I exist, you exist, this is, this him, there are stars, galaxies, and so on. The second world is the world of our consciousness. This is where we think, we love, we hate, and so on. We fear. And then there is the world of mathematics, which, you know, is sometimes called the Platonic world of mathematical forms. This is where everything you do is there. But now come the 3 mysteries. One, somehow from the physical world, the world of our consciousness has emerged. Second, the world of our consciousness, as you all are living proof, gained access to that world of mathematical forms. And last but most amazing, that world was found to provide the explanations for this world. How does this happen? Now you will notice that at the background of all of this, there is another big question, which is mathematics an invention of the human mind, or is it a discovery? Do we discover the truths of mathematics, or do we invent them? So here is what 3 mathematicians thought about this. So, do even the young people know who this is? This is G.H. Hardy, yes? So, very eccentric mathematician, and this is what he thought. He said, I believe that mathematical reality lies outside us, that our function is to discover or to observe it. So basically, Hardy says, mathematics is discovery. Mathematics is like new galaxies that were always there, and astronomers suddenly discover them. That's how mathematics is. This beautiful book was written by Ed Kastner and James Newman, and they express precisely the opposite opinion. They say mathematics, unlike the music of the spheres, is man's own handiwork, subject only to the limitations imposed by the laws of thought. Mathematics has no existence outside the human brain. That's it. Now, you will notice something very strange here. You're all mathematicians. Mathematics is supposed to be the pinnacle of precision. And this looks more like a Republican debate. I mean, they have exactly the opposite opinions. How is this possible? I'll tell you why it is possible. It is possible because the question, is mathematics an invention or a discovery, is not a question in mathematics. It is a question in philosophy. If mathematics comes from the human brain, it may be a question in cognitive sciences, and so on. It is not a question in mathematics. And this is, by the way, why mathematicians should not be the ones trying to answer this question. They, more than anybody, should know that that's not their area. So one thing I've done in the book was to actually go through history and go through some of the figures that I thought contributed to us being in this conundrum now, trying to understand these questions. And I'm going to now very, very briefly just present to you a few of these personalities. I have many more in the book. So here is Plato. And Plato, I remind you, had this famous allegory of the cave. So allegory of the cave is basically, Plato says that we humans were just like some prisoners in a cave, and we are forced to look just at one wall, and on that wall somebody projects shadows, and the prisoners see those shadows and they think that's reality because that's all they see. But in fact, these are just shadows. Now, Plato takes this metaphor and applies it to mathematics as well. Basically, he says something like, when you draw a circle on a piece of paper, that's not the real circle. The real circle exists somewhere in this Platonic world of mathematical forms. The circle you draw on the piece of paper is just some crude approximation to that real circle. So that is how this came. By the way, this is... I was when I write books, I like to go to the places where some of the key figures are, because I always find some documents, this, that. I was very disappointed to hear that archaeologists found absolutely nothing from Plato's Academy. There is nothing left, not one stone. So I went to the next best thing. Plato writes in several places that he liked to walk near the Stoa of Zeus, and that there are remains of in the ancient Agora in Athens. Maybe it's not the greatest time to go to Greece now, but I was there a few years back, maybe 4 or 5 years ago, and it was extraordinarily hot. It was the hottest summer in recorded history. There were fires all over the place. It was 127 degrees that day, but I still... Believe me, I really loved walking there at this ancient agora, thinking, here is where Plato used to walk, for heaven's sake, So, then there is Archimedes. That may or may not be him. Some think this may be a Spartan king. But in any case, Archimedes was arguably the greatest mathematician to have ever lived, when you take into account the background on which he operated. I mean, people make these games, and at the end they come up with, Newton, Archimedes, and Gauss as the three top ones. But when you take into account the background, okay, Archimedes may be the greatest. But what Archimedes did, he was the first person to really take his mathematics and to actually apply it to the universe. The Romans put siege on his city of Syracuse, and he was inventing all these incredible machines that were fighting the Romans. Now, there is one story that he used a set of mirrors to burn the Roman ships. So about 10 years ago or so, some students at MIT decided to test that. So they collected 127 mirrors, built a model of a Roman ship, and actually managed to set it on fire. Which is very, very nice, but to me, it tells me that the story was probably a myth. And the reason is that it's very nice that they managed to set it on fire. It's nice that it's possible, but first of all, I'm not sure how easy it was during the siege to collect these 127 mirrors. Second, this model was 30 feet from the mirrors. So can you imagine, the Roman ships are coming, and there is Archimedes at 30 feet placing his mirrors, and so on. It looks a bit ridiculous. So I think the story is a myth, but it can be done in principle, so that's very nice. Then there is Galileo. In 2009, we celebrated 400 years to his first observations with a telescope. And so it was the International Year of Astronomy. But Galileo did something which to me is even greater than his actual observations. He was the first person to actually identify mathematics as the language of science. And here is how he said it. Philosophy, which to him means all the natural sciences, is written in that great book, the universe. But we cannot understand it if we do not first learn the language and grasp the characters in which it is written. And then he says, it is written in the language of mathematics. So, to him, the universe is written in the language of mathematics. So to him, it's not a surprise that mathematics actually can explain the universe. Now, you must understand that this was an extraordinarily bold statement for Galileo to make, and actually he had no basis for that statement, because everything we call today the laws of physics did not exist yet. He formulated about the first ones of those. So how did he say that it was all, except Archimedes formulated a couple? But so this was a very, very bold statement. But in any case, it was amazing. Then there is René Descartes, who did a few interesting things here and there. René Descartes, I graduated in mathematics too, but I'm a physicist, and physicists don't appreciate Descartes as much. And the reason is that he was a bit unlucky to have lived not that long from Newton, and Newton had this really annoying habit of never being wrong. Descartes was wrong sometimes, so physicists appreciate him a bit less. But if you start a question by who was the first modern, and now you put a whole series of disciplines behind this, philosopher, biologist, mathematician even, and so on, physicist and so on, the answer is Descartes to all of them. So he was really clever. I just want to concentrate here on one thing he did, which I don't need to explain to you, but it is helpful if you are in New York, at the corner of 34th Street and 8th Avenue, you have to meet somebody at 59th and the 5th. It's very easy for you to get there, because you just count the streets, you count the avenues, and you get there. Well, as you know, Descartes formulated that. He basically turned geometry into an algebra by creating analytic geometry, which is, of course, phenomenal, because that is what allowed eventually for us to speak about functions, to speak about everything. A circle is suddenly not some mysterious, even as a student, I remember being mystified by this, the collection of all the points that are equidistant from another. Each one of those things, you think about the definition of a point has no dimensions. So what are we talking about even here? So Descartes says a circle, x squared plus y squared equals 4. That's a circle. So he certainly was. In addition, of course, he was this incredible philosopher, and this is usually summarized by this thing. You find this on T-shirts, cogito ergo sum, which is it's much more than it actually sounds. I mean, he was a real skeptic. He said, when I look at you now, how do I even know that you are real and this is not some sort of a dream that is installed in my brain, and so on. And then after all these, he talks about this, he gets to this thing, I think the fact that I'm doubting cannot be doubted, things like that. So an incredible guy. And then, of course, there is Sir Isaac, who in this one book managed to unify phenomena as diverse as apples falling on somebody's head, the Earth-Moon system, tides on the beaches, solar system, and so on. So after Newton, scientists became very ambitious, and for a while they thought that actually they can explain everything by mathematics. I imagine some of you still think that. Namely, there are tensions with Iran. There must be some mathematical theory that can explain that, or the stock market. We saw how well they do, right? So anyhow, they thought they can explain everything with mathematics, and for a while it looked like they were right, because there were all the Bernoullis and so on, and they were showing more and more things that they can actually do with mathematics. And then something happened, and that happened at the beginning of the 19th century. And what happened, of course, was that, the fifth postulate, Euclid's fifth postulate, was always an annoyance to many mathematicians, and they always tried to prove it from Euclid's other axioms. But they failed. By the way, I was always a theoretical physicist. I was hopeless with experiments, even as a student. But as a student, you have to do experiments. So I actually formulated the first postulate, between every two lines, every 2 points, you can pass a single straight line. I formulated that to say that among any 3 points, you can pass a straight line if it's thick enough. Now, of course, what happened at the beginning of the 19th century is that these three gentlemen, independently, Carl Friedrich Gauss in Germany, Nikolai Lobachevsky in Russia, and János Bolyai in Hungary, they all showed that actually, let me maybe just give one sentence of introduction. I mean, if there was anything that was thought of almost as a religion, this was Euclidean geometry. I mean, Kant, the great philosopher, said that space is Euclidean geometry. I mean, there was no thought that it can be anything else other than Euclidean geometry. And then these three gentlemen showed that actually they can create geometries in which the fifth postulate does not hold. And not only that they can create geometries like this, but that those geometries, namely hyperbolic, and spherical geometries, actually can describe space just as well as Euclidean geometry. So all of a sudden, there was this situation where, so of course the difference being that Euclidean was in the plane, but you could describe this on surfaces like saddles or surfaces like spheres, and Riemann, of course, unified all of that. But what happened, this was truly a disaster, actually, to the status of mathematics, in the sense that geometry suddenly, from being a truth about space, it became more like a game. Namely, you give me one set of axioms, I'll get one geometry. I can change the axioms and get a different geometry. It's like, I teach you how to play chess. I tell you the rules of chess, we play chess. We change the rules, we play a different game. But there is nothing wrong with that, right? So this was the situation. So suddenly, before there were all these Platonists that thought that mathematics is this set of divine almost truths that are out there in the Platonic world of mathematical forms, and suddenly there came these formalists who said, no, it's all a game. You just write a set of axioms, you get one mathematics. You can write a different set of axioms, you can get another mathematics which is equally valid. It's just a matter of what sets of axioms do you choose. Now, this was a disturbing state of affairs, and because it was disturbing, there came this entire group of people who were called logicists, a champion of whom was Gottlob Frege. Gottlob Frege was, in my opinion, an incredible genius. It's a pity that he was also a great anti-Semite, but he was an incredible genius. And basically, Frege said, stop here. Actually, all of mathematics comes from the axioms of logic. I can write down a set of axioms of logic and derive all of mathematics from that. So, what is an axiom of logic? I don't need to tell you, but to people who don't do mathematics, I usually say it like this. You say, either the butler murdered the millionaire or his daughter killed him. And then I tell you, his daughter did not kill him. Then you have to conclude that the butler did it, and this conclusion is independent on how old is the daughter, what is the length of the nose of the butler, or any such thing. So this is an axiom of logic. Namely, in mathematical language, it's if either P or Q and not Q, then P. So Frege said, I can derive all of mathematics. Now, all of mathematics sounds too ambitious, so he started with arithmetic. He said, I can derive all of arithmetic from a few axioms of logic. And he set out to do that. Sometimes when I give a talk like this to non-mathematicians, the thing that amazes them most is that I say that even 1 + 1 = 2 can be derived as a proof from axioms of logic and not from experience. Now, some of you may recognize what's written here. This is actually the end of the proof that 1 + 1 = 2 from this book by Russell and Whitehead. Now, this is where people get really confused. Just all this I need to show that 1 + 1 = 2? Well, yes. But, you can actually prove it from axioms of logic. So here is Frege. Now, in order to be able to do that, Frege did some, of course, very beautiful connections between logic and the theory of sets. So, just to give a trivial example, how you make a statement in logic and in sets, I can say in sets that the set of all horses is contained in the set of all four-legged animals, or I can say it as a statement in logic, if X is a horse, then it is a four-legged animal. Now, there are some things that Frege did there which are truly beautiful. For example, he showed that he can define what does it mean that two sets are equinumerous without ever defining what is the meaning of a number. So how did he do this? Well, you know this. If there is a one-to-one correspondence, then I don't need to define a number. So if every garbage can has a lid and only one, then I can say that the set of all garbage cans is equinumerous to the set of all lids without ever telling you what number means. So all of this was great, and I'm sure many of you even know what I'm going to say next, because the story is, of course, that Frege wrote this fat book on the foundations of arithmetic, and he was ready to send it to print. And when he was ready to send it to print, something truly shocking happened. And it was so shocking that even this gentleman here got completely shocked. And one way to explain that is through the sign that this barber shop puts on his shop. I shave all and only those men in the village who do not shave themselves. And that's, of course, a perfectly logical statement, because the men who shave themselves don't need the services of the barber, and the barber shaves everybody else. The question, however, is, of course, who shaves the barber? Because if the barber shaves himself, then he's one of those that shave themselves, and then he cannot shave himself. If, on the other hand, he doesn't shave himself, he's one of those that don't shave themselves, and therefore he needs to shave himself. So this is the barber's paradox that Russell wrote, and one of the solutions to do that, it can be that the barber is a woman, or the barber is from a different village, or that there is no such barber. And the whole statement is nonsense. The barber, by the way, was so shocked that he closed the shop here. Now, what Russell sent to Frege was not the barber's paradox, but he sent him this, what has become known as Russell's paradox, namely, is the class of all of those classes that are not members of themselves a member of itself or not? And these are the kinds of things that if you start a discussion on this at dinner, you will never end dinner that night. So it's a very disturbing type of thing, but of course Russell invented the paradox to show that human logic is fallible, and he succeeded in doing that. And, of course we know today that there are problems with the axioms of choice and problems with the continuum hypothesis and so on, but which I will not enter. But basically, the whole thing looked like the formalists were winning, because basically they were saying, when Frege got Russell's letter, he said, a man can hardly have something more horrible happen to him than have the foundations give way just as his book is ready to go to the print. So the formalists, thought they were winning, and because they said it's all a game. You write axioms, you can get all of mathematics from that set of axioms. Write another set, you will get another mathematics. But then, of course, something else happened, and something else happened is this gentleman, Kurt Gödel, who in two incompleteness theorems showed, wait a minute, there is no formal system of axioms that you can write down that will actually capture all the truths of mathematics, basically even of arithmetic. So this basically said, no, even the formalist dream is untenable, because, you cannot write a finite set of axioms. There will always remain statements that may even be true, but that you will not be able to prove neither that they are true nor that they are false with a set of axioms. But this, of course, raises at an even more acute level the question of the effectiveness of mathematics in explaining the universe, because you see there is this double pulsar system which has this telephone number here, and we can explain everything in that system using general relativity, which is this highly mathematical theory, and we can explain everything to better than 0.05%. So how is it possible that with a language, I'll call it, with such shaky foundations, you can actually still make it as effective as it actually is? So let me come back for a minute to this invention or discovery question. So what I argue in the book, and I'm willing to argue that with anybody, that when you ask the question, is mathematics an invention or a discovery, you actually do not pose the question well. Because if you ask, is mathematics an invention or a discovery, the natural assumption is that the answer has to be this or that, and that it cannot be something else. But actually, I claim that the answer is something else. And what that something else is that mathematics is actually a very intricate combination of inventions and discoveries. And let me give you first a broad thing, and then I'll just give you some examples. So the broad thing is that we actually invent the concepts, and then we discover the relations or theorems among those concepts. Now, this is something that actually mathematicians have the hardest time to accept, because what I claim is that even when you talk about a straight line, that as a concept, that's an invention. This does not mean that there are no straight lines that you see in nature. But as a mathematical concept, it is an invention. So here I have a few examples. So, for example, Euclid and the Pythagoreans before him defined the golden ratio, which is, that the long to the short is the same as the whole line to the long. And you can easily show that this gives you this number phi, which is 1.618 and so on. This is an invention. Why? Why is it not a discovery? Because you can divide a line in an infinite number of ways. And yet you don't talk about all those ways. You talk about the golden ratio because Euclid decided to name this particular division and to start studying it. Indian mathematicians never defined the golden ratio, and it doesn't appear in their mathematics. It actually appears in some Indian poetry for a different reason, but doesn't play much role in their mathematics. Then I give another example, which is the Fibonacci sequence. So Fibonacci arrived to it, well, his name was Leonardo of Pisa. He arrived to it from this silly rabbit problem, okay? But he found this series where every number is the sum of the previous two. This is an invention. I mean, there is an infinite sequences I can invent. I can invent a sequence where each number is the sum of the 17 numbers before it, or the 13 before it plus the 4 after it, or whatever. But you talk about this sequence because as a concept it was invented. Now let me give you an example of a discovery, and it's a real discovery. When you do the ratios of consecutive numbers in the Fibonacci sequence, the ratios converge to the golden ratio. This is a discovery. Why? Because humans had no choice in this matter. Once they defined this and they defined this was forced upon us. So this we couldn't invent anymore. This was a discovery. So basically, again, mathematics, we invent some concepts and then we discover all kinds, like you can think of a million things, imaginary numbers. They came about because people tried to solve the cubic. But they didn't have to invent that concept. But they invented the concept. Once the concept was invented, you couldn't do almost anything that you guys do without them, right? Anymore. So now you discovered a whole world with those invented concepts. Was our mathematics inevitable? Well, if there was anything inevitable, it had to be the natural numbers, right? 1, 2, 3, 4, everybody had to invent this, right? Well, not so fast. Imagine that intelligence resided not in humans, but in some isolated jellyfish at the bottom of the Pacific Ocean. All that this jellyfish can feel is the temperature of the water, the motion of the water, and the pressure of the water. Would this intelligent creature have invented the concept of the natural numbers? I'm not so sure. There was nothing to count. Its world was a world of continuum. It was not a discrete world. So I don't think that our mathematics was even inevitable. I mean, it may have been inevitable for us, but not that it is inevitable in general. So why is mathematics as effective as it is in explaining the universe? So this is a tough question, and I deal with that at great length in the book. But I want now just to give you a hint as to how you might think of the problem. And I'll give it with some silly experiment. Here, I have a vase, and I have a collection of pebbles. And the experiment is, I take some pebbles. I take 3 pebbles, I put them in the vase. Then I take 4 pebbles, I put them in the vase. I want now a theory that will predict to me how many pebbles I have in the vase. So you say, well, it's arithmetic addition. That's the theory. 3 plus 4 equals 7, right? Very simple. Now imagine that instead of putting pebbles in this vase, I'm actually pouring water from a bottle into the vase. So I pour water 3 times, and then I pour water 4 more times. Can I say I have 7 water in the vase? Of course not. I would actually use a completely different concept, right? I would use perhaps a concept of the weight of the water or the volume of the water or something, right? In other words, when we try to explain physical phenomena, we don't choose our mathematics arbitrarily. We kind of choose the type of mathematics that we already have some feel might work. So that begins to tell you something a little bit about this effectiveness. Now, what is it that guarantees that the mathematical model exists at all? So the answer is that nothing guarantees that. And in fact, I can prove that to you. For example, suppose that somebody asks me, will we be able to predict the weather to the level that we will know what each individual atom in the atmosphere does? You may think, why not? We know the equations of motion for atoms in the atmosphere. And so if we will have a large enough computer that we will input all the initial conditions, we'll be able to solve for that. Maybe we cannot do it today, but in principle, maybe it can be done. No. And I'll tell you why. The equations of motions of the weather actually is a chaotic system, which means that it has infinite dependence on initial conditions. Which means that in order to actually solve the equations with predictability, you need to know to infinite precision the position and the velocities of each atom at the beginning of the experiment. Now guess what? Quantum mechanics tells us that we cannot know with infinite precision the position and velocity of one atom, because there is an uncertainty principle, let alone of all the atoms in the atmosphere. So I can guarantee you that we cannot solve this problem with a mathematical model, which does not mean we shouldn't have better models for the weather. Of course we should, and we are, and we continuously improve those, but this particular problem cannot be solved. So I want to finish now with a quote from Bertrand Russell, which I think is just, when I first read this some years back, I mean, it blew me away how clever I thought this was. So it's a little bit lengthy, but bear with me and let's read it. So he talks about philosophy, but you can say the same thing about mathematics and other things and so on. So he says, philosophy is to be studied not for the sake of any definite answers to its questions, since no definite answers can, as a rule, be known to be true, but rather for the sake of the questions themselves, because these questions enlarge our conception of what is possible, enrich our intellectual imagination, and diminish the dogmatic assurance which closes the mind against speculation. But above all, because through the greatness of the universe which philosophy contemplates, the mind also is rendered great and becomes capable of that union with the universe which constitutes its highest good. Thank you.